Welcome to learning to do t-tests and comparison of two means with R. For this lesson, you will need three packages: LME4, Tidier, and lmer test. So I'll give you a moment to either turn me off and pause me and download these, or go ahead and download them now. Okay. Once you have these packages installed, we'll call these up as we need them. What we're going to do is we're going to simulate some data right now, and let's perform an experiment where we have 30 patients, and they're going to be numbered 1 through 30, and we're going to give them, let's just say, some coffee. And we're going to measure their heart rate before and measure it 1 hour after having 2 cups of coffee. Let's get crazy. As I drink my 2 cups of coffee. Okay. So the way to simulate these data, we're going to create an ID, which will be your patient ID. And it's 1:30, which will create a vector from 1 to 30. All right, for the before data, we're going to create 30 random points with a mean of 70 and a standard deviation of 10. They're going to be from a normal distribution, but randomly selected. So the mean may not necessarily be 70, but it's from a mean of 70. We're going to sort those, and we're going to do the same thing to simulate after the effects, and we're going to bump up the heart rate by 15 beats a minute, but keeping the same standard deviation. Okay, so let's go ahead and we'll run this. And what this part of the code does, we're going to create heart rate wide, HR wide, and we're going to create a data frame where we bind together these vectors, ID before and after. What does this look like? Okay. So here's what the data looks like. Okay. So here's our ID, our patient ID, the heart rate before and heart rate after. Since this is random data, your data will not look like this, okay, but should have roughly the same distribution. All right, so what we want to do is do a t-test to compare the before versus after. And for right now, we'll consider these independent. And the way to code this is simply t.test. And then our 2 variables separated, in this case, by a comma. And let me just say, we're calling this wide because our data is in wide format. And that's because we have before and after here. And if you imagine if we kept recording data, we would have another column, and the data set would just get wider and wider. Okay. So doing a t-test with these columns being treated independently, all we need is t-test in the 2 variables. Let's just remove this. All right. So t.test and our 2 variables brings this up, a Welch's 2-sample t-test. What it provides for you is the t, so this is your sample statistic, the degrees of freedom, okay? And if you note, it is not a nice round number. It's actually an estimate of the degrees of freedom, and a p-value. This p-value, if we use an alpha of 0.05, then this is much less than that. So we can reject our null that the 2 means are equal. Okay? And we knew that because we created the data. All right. This is the 95% confidence interval of the differences between means. Okay, so if we repeated this experiment 95% of the time, the differences between before and after would occur between these two numbers. And here's the mean of the estimated mean of before, and here's the mean of after. Okay. So that's a t-test in a simple wide format. I would not suggest using a wide format unless this is your one and only experiment. A nicer way to form your data is to have it long format, is to have the before variables data stacked on top of the after data. You're going to need to call up tidier. Okay, so we're going to call up the library tidier. The tidyverse is a suite of packages, including tidier, that's supposed to be updated and improve data analysis. Okay, here's how we're going to convert HR wide, and let me just show you what that looks like. So we'll pull that up. Okay, what we want to do is stack these data on top of or below, doesn't matter, on top of this. But if this is patient one, and this is that person's heart rate before, and this is the heart rate after, what we want to make sure is this one is indicated before and after if we're going to move this above and below. Okay, so here's the code we're going to use. We're going to create an object called heart rate long, HR long. We're going to use the function gather. So what that does, it's going to mush things together. It's going to go to the data HR wide, and it's going to create two variables. One is going to be the period, okay? And the period will be the sample period that will be indicated by saying before or after. And we're going to create a column called heart rate, which will be these data, okay? So we're going to create these two columns, and we're going to reference before and after, okay? If we had measured, say, sample 1, sample 2, sample 3, sample 4, and wanted to stack those all, we would have sample 1 to sample 4. We just have before and after. So this is the columns we're going to gather, and factor key equals true, which means when we have the period time, that's going to be considered a factor. It's going to force it to become a factor. All right, so we'll run that, and now let's take a look. All right, go to the top. Here's our ID, so it should be 1 to 30. All the befores, here's their heart rates. And it took the afters and put that under, and here we have the ID number of the patient and their data. So for every 1 before, there's a 1 after. For every 7 before, there's a 7 after, and so on. All right. So the one thing we didn't do this last time was, if we're doing t-tests, we should make sure that the data are normal, because that's one of the assumptions. What I'm doing here is I'm creating a histogram of the heart rate, but we have to do it for each group. So what we have to do is reference the data in long format, and we're going to pull out the group before, and then we'll do it again with after. So let's run before. Okay. So here's the histogram of the before data. Looks relatively normal. Here's the after, does not look that normal. So if you remember, we created this data from a random normal distribution. So even though the data is pulled from a normal distribution, you may not necessarily get, especially with a sample of only 30, you may not necessarily get a nice, smooth, normal distribution. Okay. So this does look relatively normal, and there's other ways we can check for that as well. The other assumption is that the variances are equal if we do a straight up student's t-test and not a Welch's test. So to do a test of variance, which is an f-test, we're going to compare the variance in the after compared to the variance before. And that's just a var dot test, so variance test. So we'll run that. Okay. And here's the result of that. It's an F test. Here's the F. Here's the degrees of freedom. Okay. So it's 29 in the numerator and 29 in the denominator. So it's 1 minus the sample size for each, the top and the bottom. The p-value is 0.8928. You will not get the same number, right? Because we were dealing with different random numbers, but you should not get a significant result. So your results should look something like this. Although, you know, statistically speaking, 1 out of 20 times we do this, we make it a p-value of 0.05 or less, right? Okay, so we have normal data or variance is equal. We can do a student's t-test, okay? So now that our data is in long format, the code is still t.test, but when you use long format, we use a tilde. So we're looking at heart rate by or distributed as the period time. Okay, so let's do that. Okay. So it runs a Welch's two-sample test. If we wanted the variances to be equal, we would add, I'm doing this below, equal var equal true. Okay. And that forces a student's t-test, even though it says Welch's two-sample test. And if our variances were unequal, we would have equal variance equal false. Okay? And we would run that test, and you should get more or less the same results. Okay, so running this, we should get pretty much the same results. Okay, we get a p-value that is, we can reject the null hypothesis that our means are equal. Take note that the degrees of freedom here are 57.9 or 58, okay, because it's 60 minus 2, or actually it's 30 minus 1 plus 30 minus 1. Okay, so we would report the t, the degrees of freedom, and the p-value. Now here's the thing. We've been doing this wrong because we actually measured the same patient twice. So what we actually have is a paired t-test. And conducting a paired t-test is very straightforward. In R, you just add this argument, okay? And the argument is paired equals t. Once you do that, it's a paired t-test, and that should change several things. So when they're treated independent, notice that the degrees of freedom are 58, okay? We're gonna pair, let's see what happens. Okay, paired t-test. The t is different, And now our degrees of freedom are 29 because we didn't have essentially two groups of 30 with those groups being independent. We actually had a group of 30 that we measured twice. So that lack of independence means we lose degrees of freedom. Okay, when you lose degrees of freedom, your p-value is also smaller. So this is exceedingly small p-value. Still, we reject the null that the means are the same. Okay, and here's the mean of the differences, at least in my sample. So the mean of the differences, so that would be for each patient, you subtract the before from the after. Okay. All right. Now let's say we wanted to run a Wilcox test. So that we're going to use our same data and we're going to do a paired Wilcoxon test. And that code is simply wilcox.test. And it's the same, otherwise the same syntax. So we're looking at heart rate by the period before and after. And we're going to pair it. Okay. Since our data are not parametric, we're assuming on non-parametric data here, which simply means we don't know if the data are normal or not, or we know that they're not normal. All we would report here is the V and the p-value. Okay, and this is testing the null hypothesis that our ranks are the same. Okay, to plot our data. Now that we have our tests and you report those tests in the methods, you want to produce a plot. The plot is, we're going to use the same syntax that we use to create the analysis. Is we're going to use a tilde. If we wanted to plot X's and Y's, we use a comma, but we want to plot heart rate by the period. Okay. So if you remember, we told R to produce a data set where the data were normal, randomly selected from a normal distribution with a mean of 70. So there that is. With the after being, I think we said 85. And so that's where our data is. These lines represent the median response. And then this contains 50% of the data of the box, okay? And then the whiskers contain about 95% of the data, okay? So 95% of the data are occurring within this. And since the whiskers are more or less symmetric about the median, it looks like these data are relatively normally distributed. All right. So if we look at this, we have before and after lowercase, this HR long $ period. This is not the best looking graph. So let's fix that up and we'll produce another plot. We're going to fix the Y label to be heart rate, beats per minute. We're going to fix the X label and we're going to add names to that X label being before and after. So let's see what this looks like. Okay, so here's our new plot. Okay, before and after, sample period, heart rate, beats per minute. So that's a lovely graph. Okay, so that's a simple t-test and Wilcoxon, some rank tests, but let's try something slightly more advanced. Let's look at comparing means as a as a model, okay? And the function we're going to use is generalized linear models. Generalized linear models can handle a whole suite of different data types. And the way you indicate the type of data, okay, or the errors you expect is by saying family equals. In our case, we're going to assume that our errors are distributed normally, so we're going to indicate that with Gaussian, but we could say Poisson or binomial or several other different families, okay? So the syntax is the same as a t-test in long format. You cannot do GLMs in wide format as far as I know. So what we're going to do is we're going to call this analysis an object, and that object we're going to name A. So we'll go ahead and run that. And if you notice, once we do that, nothing happens, okay? So, but no errors, which is good. So to get the output from a GLM, a generalized linear model, we're going to call it up with summary and then the name of the model. Okay. So the output looks like this. It gives you the formula where it's heart rate distributed by period, the family, Gaussian, so our errors are normal. Gives you some output of the residuals. But here's what we're interested in. So the heart rate, the overall average is 69, okay, or 70. So what we use is the before, okay, and that is 69.329 right there. And this p-value, okay, is not that interesting because we don't expect that the baseline, the before, to be 0. So this p-value represents the first coefficient, the estimate, right? The intercept. Is it different from 0? We can reject it, but that's not very interesting. We kind of knew that already. Here's what we're interested in. The effect of being in the period after, okay? That estimate is 11.352, okay? That means that being in period after, on average, increases your heart rate by 11. So if you add 11 to 69, you should come up with the average, which is just over 80, okay? And this is the p-value, okay? So this p-value represents the probability that, actually it's testing the null, that there's no difference between these numbers. So this is the probability of getting this estimate, giving there's no difference, and we can reject that. Okay, so we have significant data, and 11.352 is significantly higher than the heart rate before. So that's how you interpret this. We're going to add 11.352 to 69, and that'll give us our average response for the after. Okay, so this is what I mean by the difference between, as we're talking about in lecture, that the goal of hypothesis testing, which you use a t-test, is completely different than a modeling approach. In a modeling approach, we want to know what the difference is, what's the effect, right? So having 2 cups of coffee and our simulated data increases your heart rate by 11 beats per minute over having no coffee, okay? These 3 asterisks tell you at what level. So that means we are greater than this number, okay? So, which is indicated here, right? So we could just copy and paste this into our results very nicely. All right. So one issue is that this analysis assumes that these two things are independent. So we essentially ran a student's t-test, an unpaired student's t-test. Okay, that's not what we want to do because we know these data are not independent. So what we need to do is run a mixed model, okay? Our mixed model. So a mixed model means you have a random effect, okay, and a fixed effect. And a fixed effect means it's the same for those subjects all throughout the universe. And a random effect means the random effects take into account the non-independence, okay, that you randomly selected those particular levels, okay? So in our experiment, the effect of coffee, the before and after effect of coffee is our fixed effect. Our random effect is the fact that we use the same patients, right? 30 patients. These are random 30 patients. That's one way to think about it, okay? What we need is, again, using the package lmer4, we're going to call up that library, okay? And we're going to use the library lmer test, okay? Not dot test, just lmer test with a capital T. Okay. The mixed model approach, that syntax looks a lot like GLM, right? So instead of GLM, we have lmer. Okay. And we have the same thing. We're interested in heart rate as a function of period. This syntax right here, in parentheses, what we want to have is, so this is the fixed effect plus the random effect. And the random effect we denote, in this case, we have a 1 coefficient, and then we have this bar, okay, vertical bar. So on some keyboards, this would be in the very northwest quadrant. Mine's in the very northeast quadrant, okay, with the backslash. And then ID. And ID is the variable that unites the before patient, indicating it's the same as the after patient, okay? And we're going to pull out the data we pulled out separately. So we could have HR long in here, but it was a little bit simpler just to pull this out, put it here so I could show you this. Okay, so we'll run this. And again, because we did this analysis and created this variable B, we have nothing here to show, but and actually let me show you what summary B looks like. All right, so here's the summary of B, and the important things are, here's our fixed effect, right, the period after. Again, here's our degrees of freedom, okay, which is correct. So that's 30. And here's the p-value. And that is the thing we're most interested in. A quick summary of our results is if we use ANOVA. So if we use ANOVA, that will give us a summary of these results and give us the sum of squares due to period, give us our mean squares, okay? And this is the degrees of freedom numerator, degrees of freedom denominator. This is our F value for the test, and here's our P value of the results. Okay, so one of the assumptions of these t-tests is that the results are normal. And one way is to plot the analysis. So I just want to see what happens when we plot the analysis. Okay. So we're not plotting the raw data as we did above to create nice graphics for our output, the box plots. When you plot an analysis, oftentimes you'll get an analysis of the residuals. So Pearson residuals, what they do is they take each residual, and if it's they standardize it to 0. So regardless of whatever mean it is, they center it, that particular mean on 0, and then standardize the residuals. So all these residuals above the line, they indicate errors that are above that particular mean and those below. And what you look at is for a pattern. And in this case, looking across, I see a nice scatter. So I don't see any sort of patterns indicating that there's something wonky with the data. What you want is essentially something that looks like random points with an equal number above and below. If you have any sort of curvature to residuals, it may indicate that you have something else going on in your data. Okay. If you do a modeling approach, you want to report the goal, right? So if you do a hypothesis testing, you want to state your null and then your alpha. If you're doing a modeling approach, you want to say that you're interested in the effect of your particular treatment and how that affects things. So in this case, we'd report that our increase in heart rate was about 11 beats per minute. You also want to provide the p-value of that effect, the exact p-value. And of course, you'd want to produce box plots as well to show those differences. All right, and that's it. There's your whole family of t-tests. Hopefully that's everything you'll need. So here's hoping for simplicity in your life.